We'll use gradient descent for minimizing the loss. We need to compute gradients of the loss with respect to weights and biases. So specifically we calculate partial derivative of loss with respect to weights and partial derivative of loss with respect to biases. Here WLJ is weight connecting neuron I from layer L-1 to neuron J in layer L, and BLJ is the bias of neuron J in layer L. Backpropagation is an efficient algorithm to compute the gradient of the loss with respect to the weights. At the heart of the algorithm is the chain rule for derivative. So in order to compute these two quantities, we'll be using chain rule. So to understand how to compute gradients in a network, let us consider a very simple network for regression problem. Here we have a single input, a single hidden layer with single neuron, and output layer with a single neuron. In order to compute the gradient, we first need to compute the loss on a training example. So here is our network where in layer 0, A0 is equal to X, the input feature. In layer 1, we first compute the pre-activation Z1 as W1 into A0 plus B1. Then we compute the nonlinear activation of this Z1 to get A1, which is activation from layer 1. This activation is fed into layer 2 where we first compute the pre-activation Z2 as W2 into A1 plus B2. Then we compute the nonlinear activation of Z2, and that is A2, and since it's a regression problem, this A2 is the predicted output, which is Y hat. Since we have Y hat, we can now compute the loss for this training example because we know the actual label and the predicted label, and the loss is computed as half of the square of difference between the predicted value and the actual value. So let's look at the gradients that we'll be computing for different layers. For layer 1, we'll be computing partial derivative of loss with respect to W1 and B1, whereas in layer 2, we'll be calculating partial derivative of loss with respect to W2 and B2. Let's first calculate partial derivative of loss with respect to W2, and here we make use of chain rule. So W2 and L are connected first through the pre-activation and then through the nonlinear activation. Hence, first we calculate the partial derivative of loss with respect to the nonlinear activation A2, and then multiply that with partial derivative of A2 with respect to Z2, which is pre-activation, and then the partial derivative of loss Z2 with respect to W2. This is how we compute the loss, the partial derivative of loss with respect to W2. And this turns out to be Y hat minus Y into G dash of Z2 into A1. In the same manner, we can compute partial derivative of loss with respect to W1, and is calculated as the partial derivative of loss with respect to A1 into partial derivative of A1 into with respect to Z1 into partial derivative of Z1 with respect to W1. The partial derivative of loss with respect to A1 is computed over here, and it turns out to be Y hat minus Y into G dash of Z2 into W2. We substitute this value in this equation and obtain the partial derivative of loss with respect to W1, and it is this particular quantity into G dash of Z1 into A0. So we know that we have activations that pass through pre-activations, and in pre-activations we use weights to calculate the linear combination. So let's say AL of G is the gradient of loss with respect to activation, ZL of G is gradient of loss with respect to pre-activation, and WLG is the gradient of loss with respect to weight. So if ALG is already known, we can compute the rest of the gradient. So ZLG is equal to element-wise product of ALG and G dash of ZL. WLG is the matrix product between AL minus 1 transpose into ZLG, and AL minus 1G is the matrix product of ZLG with WL transpose. These equations will make more sense if we compare them with their forward pass counterparts. So in forward pass we calculate the pre-activation ZL as the product of AL minus 1, which is activation from the previous layer, into weight matrix of the current layer plus BL, which is bias vector of the current layer, and AL, or the activation for the current layer, is calculated as nonlinear activation of ZL, or the pre-activations. Now you can see that ZLG, the gradient of loss with respect to Z, is calculated as ALG element-wise product with G dash ZL, whereas WLG, or the gradient of loss with respect to weight, is calculated as L minus 1 transpose into ZLG, and L minus 1G is computed as ZLG into WL transpose. For a moment, think all of them as scalars, but we can show that these equations are the matrix equivalents of the chain rule. All gradients in the hidden layers depend on the gradient of the loss with respect to the output activation ALG, and this depends on the nature of the loss. In case of regression, ALG is equal to y hat minus y, whereas in classification it is an element-wise product between the actual labels and the predicted labels. The activation function in the final layer for regression is just the identity function. There is a slight abuse of notation. ALG and ZLG are vectors. So ALG is y hat minus y, and ZL of G is G hat of ZL, an element-wise product with ALG, and this is nothing but ALG. In case of classification, the activation function in the final layer is a softmax activation. So ALG is equal to the element-wise product between the actual labels and the predicted labels, and of course negative of that, and ZLG is y hat minus y. Let's look at procedure for backward propagation or backward pass. So here we have listed an iterative algorithm to compute the gradients given the actual labels and the predicted labels. So note that G is identity for the output layer because we are dealing with a regression problem, and therefore ZLG is equal to ALG. So we initialize ZLG to y hat minus y, which is the difference between the predicted value and the actual value, and we run a loop from layer L, which is the output layer, to the first layer. So in each step we compute WLG as L minus 1 transpose into ZLG. BLG is equal to ZLG transpose into a vector of 1 of size n. Then L minus 1 G is equal to ZLG into WL transpose, and ZL minus 1G is equal to L minus 1G element-wise product with G hat ZL minus 1. For classification, G is the softmax function for the output layer, and ZLG is equal to y hat minus y. And we have pretty much a similar procedure like regression for the backward pass. We now have all the ingredients to completely specify the learning algorithm for neural networks. Let theta, the capital theta, refer to all parameters in the model, and let us define the following function. So we first perform a forward pass on the input feature matrix, and we obtain y hat, which are predictions. Then we compute loss by comparing the actual values and the predicted values, and then we perform the backward pass with the actual values and predicted values. If we decide to train neural network for epochs, the algorithm is as follows. So first we initialize the parameter vector theta by drawing it from a normal distribution with 0 mean and 1 standard deviation. For in every epoch, we first run a forward pass, then compute the loss, and then we perform the backward pass. And in backward pass, we basically get the partial derivative of the parameter vector, and we use that to update the parameter vector by multiplying this partial derivative with learning rate alpha. So the new value of theta parameter vector is the old parameter vector minus alpha times the partial derivative of the loss with respect to parameter vector. So the question is, why did we not initialize all parameters to 0? This is an important point, and let's try to understand if we initialize all parameters to some constant value. Since the incoming weights are the same for all neurons in a layer, there is nothing to differentiate between two layers. This symmetry means that we'll evolve them identically and will not learn different things if we initialize all of them to a constant value. So setting all weights to a constant value, especially 0, is a bad idea for neural network. That's why in our implementation, we have sampled the weights from a standard normal distribution. Let's look at overfitting issue in neural network. Let's take a simple 3-layer neural network for MNIST classification problem with the following architecture. We have 784 neurons in the input layer, we have 50 neurons in the first hidden layers and 10 neurons in the output layer because we are trying to predict one of the 10 classes for each image. Let's look at the number of parameters. So in the input layer there are no parameters, whereas in the hidden layer we have 39,200 parameters or weights, and in the output layer we have 500 weights. We have 50 biases for hidden layer for each of the 50 neurons, and we have 10 biases for output layer for each of the 10 neurons. So total number of parameters are 39,760. So with just one hidden layer, we have a model with nearly 40,000 parameters. This number will quickly blow up as we add more hidden layers. So neural networks are thus prone to overfitting. There are two methods to regularize the model. Either we use L1 or L2 regularization, as we have been doing for all other models, and second is dropout. Dropout is a method that is particular to neural network, and we will study that in a bit more detail in this presentation. Whereas L1 and L2 regularization that we have seen in other methods, and they will apply in the similar manner to neural networks. So let's discuss about dropout. Let's consider the following network with one hidden layer. So in this network, there are 4 neurons in a single hidden layer, there are 2 neurons in the output layer, whereas in the input layer there are 3 neurons. In each iteration of gradient descent, we randomly choose half of the neurons in the hidden layer and drop them out of the network. So here these 2 neurons are dropped, and when we say neurons are dropped, the subsequent connections are also dropped. So now we have a modified neural network with lesser number of neurons in the hidden layer. Then we perform a forward pass and backward pass on this modified network and update the weights. So we keep repeating this at every epoch. At inference, we use full network but halves the outgoing weights from the hidden layer. This is because only half of the neurons were active during the training. So you may wonder, why does dropout work? So during the training phase, dropout can be seen as producing multiple networks, each having a different number of neurons in the hidden layer. At test time, we can think of the output of a network as averaging over the result of all these networks. There is a key difference between two methods of regularization. L1 and L2 regularization modifies the loss function, whereas dropout modifies the network. So in this video, we studied about artificial neural network. We specifically studied about gradient descent procedure for training the neural network, and we also studied backpropagation, which is mainly used to calculate partial derivative of loss with respect to weights and biases. We also studied how to regularize neural network because they are prone to overfitting. There are two methods of regularization, L1 and L2 regularization, which we are familiar with, and we studied a new method of regularization, which is dropout.